I'm Nadia Hussein. I'll be your instructor for this class, and this is Dr. Jessica Fries. She is the coordinator and project manager. So without any further ado, let's get started because we have only like 1.5 hours and have like 20 slides to show you guys. So are any of you guys familiar with AI at all?
I do.
Just in the scope of ChatGPT and like Gemini and stuff like that? Sounds good. All right. So the goal of this course is it's an introductory course, so I won't be going that deep with you guys. So I'll try to immerse you guys as much as I can. Okay, so like, I'll immerse you with this information as much as I can. And then I'll give you homework for tonight. And then on Thursday's class, there's going to be a quiz. All right? Awesome. Let's get started. So I introduced myself. I introduced Jessica. And we're going to be using Google Classrooms, as you guys saw. And you guys can see the screen, right? Everything? All right. So the quizzes are going to be 30% of the grade. The homework, another 30%. The project is going to be 30% of the grade also, and attendance 10%. Okay, are we clear? Good on that? So just pay attention. In education, you get what you give. Get curious, ask questions early and often. Let us know if you guys want to learn more about the topic. We can adapt and provide additional resources. Dr. Fees has taught this material to students from middle school to professors at top universities. So let us know if you guys need any help with it. So let us start. Okay, I have the notes in for you guys also. So I'll have the whole lecture for you for your access, so you can access it and access the notes. All right. So what is AI? AI stands for artificial intelligence. AI refers to machines or computer systems that can perform tasks that typically require human intelligence. At our level of human intelligence, we're trying to make computers at this level of intelligence, right? Okay. These tasks include things like recognizing patterns, learning from experiences, past, present, solving problems, and even understanding languages, foreign languages of other people, So the key abilities of AI systems is learning. AI can learn from data and experiences. Okay. Reasoning. AI can make decisions based on information. Like us humans, we make our decisions based on information we have, right? All right. Problem solving. AI can find solutions to complex issues, often faster than humans. You guys, of course, know that because if you guys use ChatGPT, you know how fast it is, how fast it can solve problems. All right. Examples of AI in everyday life, voice assistants like Siri on your iPhones, if you have an iPhone, or Alexa for Amazon. Pretty sure you guys are familiar with those, right? Self-driving cars, which they're working on right now, doing a lot of work on that all over the world, self-driving cars. Like Teslas right now, they have self-driving capabilities. That's also AI and machine learning. Video games that adapt to players' skill levels. More into video games. You guys play video games at all? Video games, also encompass a lot of AI. All right. History of AI. Some early concepts in the 1950s, Alan Turing, a British mathematician who asked the famous question, can machines think? He developed a Turing test, a way to measure if a machine's behavior is indistinguishable from a human's behavior. You know what I mean? Clear? So, between the 60s and the 70s, early AI programs were created to solve specific problems, like playing chess or solving math equations. Very simple stuff compared to what we have now, right? Shaky, the robot, one of the first robots with AI that could move and make decisions based on its surroundings. And then we're talking in the 60s to the 70s. Well, that's like a long time ago. So imagine what we have now, right? And in the period between the 80s and the 90s, AI experienced setbacks, also known as AI winters, because technology wasn't advanced enough to support complex systems, right? Development of expert systems programs that could make decisions in specialized fields like medicine. So talking about systems that can make their decisions on their own. You know what I mean? That's good. Now into the 2000s, that's going to boom. And AI has made a comeback due to advancements in computing power. We now have better GPUs, better hard drives, better processors that can take on all this very complex stuff. No? Okay. Come back, advanced computer and the availability of large data sets. So now we have data sets that are terabytes and petabytes. So it's like it's unimaginable, right? A lot of very, very high storage space. Talking petabytes sometimes, like you know what a petabyte is, like 1,000 terabytes. A terabyte is 1,000 gigabytes. You know what I mean? So it's like, imagine that. It's crazy, right? Yeah. So modern AI systems now power search engines like Google. Of course, you guys know Google. Social media recommendations, and many smart devices. So it can recommend stuff to you based on your interests and the stuff like stuff you searched before on YouTube. It's going to show you stuff based on your interests, right? You don't know how it's happening, but it's all happening in the background, right? You see the front end, which is like YouTube, which is what you're using, right? And then these recommendation systems, they build very complex models. All right. So how does machine learning fit into AI? Machine learning is a branch of AI. Okay. So like we're not saying machine learning itself is AI, it's just a branch of AI. Okay. Instead of programming every task, machine learning allows computers to learn from data. So machine learning, we're giving the computer data and certain patterns, and it's learning from that data and patterns, and then it improves their performance over time. Just like humans, right? You train on something like let's say you're doing karate or something, it's not going to be the best the first time, right? So it's the same exact process that we humans have. If you're playing karate for the first time, it's not going to you're not going to be a professional, but after 10 months of training or something, you're then a professional at karate. That's the same exact concept. All right, how it works. You give a machine lots of examples, the data we talked about, and then it finds patterns or rules without being explicitly told what to look for. So it's looking for patterns in what let's say an example in like clustering. We're going to be talking about that later. Like you have a data set which has like tomatoes, pickles, milk, this and that. And then, it looks for patterns to put you in a certain customer category, right? So you're this kind of customer that buys milk and eggs and this. The computer is looking for these patterns to make these classifications. All right. Instead of programming them, every task machine learning allows us to learn from data. You give a machine lots of data. The more data you give a machine, the better your results are going to be, right? And it finds patterns and rules. Example, teaching an AI to recognize pictures of cats by showing it thousands of images instead of describing what a cat looks like. So we're just giving it a lot of images of cats, right? And it knows this is a cat from all these images we showed it. It's going to train itself. Face recognition when you open your phone? It's the same exact idea. You train the phone to know the pattern of your face, your eyes, your face, everything, right? Same exact concept. All right. Relationship between AI and ML. AI is the big picture. Like I said, ML is part of AI. AI is the bigger story, right? right? AI is the big picture, and ML is a tool used to make AI systems smart. All right, think of AI as the brain and machine learning as the method that helps the brain get better at certain tasks, right? So like I said, the brain, like the karate example, your brain keeps picking up the moves. The more you train on them, the better you get. You know what I mean? Same exact concept with computers. That's how computers work. Same exact way, like the human brain. All right, next slide. What is and isn't artificial intelligence? Talking here, simulating human intelligence. Human intelligence, which encompasses rationality, optimality, and neuroscience. Right? Neuroscience, we're talking here how the brain works, because that's how they got all this knowledge from studying the human brain. Right? Are robots AI? Well, they are, because they use the same exact concept. Because we're teaching a robot in the same way. Right? Gotcha. All right, simulating human intelligence. The goal of AI. The main goal of AI is to simulate human intelligence, basically to make machines think and act like humans. So we're trying to make machines think and act like humans in this scope. How does AI simulate human thinking? Learning. Just like humans learn from experience, like studying or practicing, AI can learn from data and improve over time, like I said. You're constantly giving it data and it's improving. Decision making. AI tries to make decisions based on the information it gets, right? Much like how we use logic or reasoning in solving problems, right? Solving problems. AI can take on complex challenges and find the best solution, similar to how humans might approach tough math problems and puzzles. AI can do all of that. Examples of simulating human intelligence, chatbots. ChatGPT, of course, you guys use that. That's having conversations with people, like you're having a conversation with the computer, right? It answers you, and then you ask it another question, it answers you back. AI assistants like Siri and Alexa, like we said, they understand and respond to commands. All right, how does it simulate human intelligence? Like we said, human intelligence encompasses rationality, optimality, and neuroscience. For rationality, being rational means you use logic and reasoning to make decisions. You're not just making a decision, just like that, you know what I mean? You use logic and reasoning. You think about it first. Human and AI try to be rational by analyzing facts and making the best possible decisions based on available information. AI uses this same approach. So it thinks before it gives you an answer. It doesn't just give you an answer like that, as we humans do. Optimality refers to finding the best or most efficient solution to a problem. So that's what optimality is. We're trying to find the best solution for a problem, not just any solution for a problem. AI is designed to find the optimal answer, sometimes even faster and more accurate than humans. And I'm sure you guys have been exposed to that, right? Neuroscience is the study of the brain, of the human brain, and how it works. AI researchers study how the human brain processes information and uses that understanding to design AI systems, like I told you guys. They study the human brain, and it's built on the same concept of human neurons. You guys know biology, right? Studied neurons, neuroscience, biology. Like how the neurons work in the brain and how they have connectors, and then it's the same exact concept, We'll get to it later. They're modeled after how brain cells work. Brain cells, like I said, they have like these connections in between them, and they work in parallel. And the human brain is just amazing, and we get that knowledge from that. So our robots, AI. Not all robots are AI, but they can be. Robots are machines that can perform tasks, but they don't always have intelligence to think on their own, right? And make their own decisions. For example, a robot vacuum cleaner moves around your house, but it might not be intelligent unless it uses AI to learn and improve its cleaning routes, right? It knows only one thing, to go around the house and clean. It doesn't have intelligence. But we're right now they're working on making robots that are intelligent. You can sit and speak to and tell it, you know, do this for me and do that for me. A lot is going on in this industry, basically. Robots and AI work together. When a robot uses AI, it can make smart decisions and adapt to changes in its environment. Example, an AI in a factory like here, see how these robots are assembling that car right there? Yes, that's an example of it, right? It can adapt to changes in its environment. Example, a robot in a factory might use AI to improve its efficiency and avoid obstacles, right? And also it goes through like humans get tired, a machine won't get tired. So you can produce a lot, you can get a lot of production. Difference between robots and AI. AI is the brain that makes decisions and learns, right? Robots are the body. So basically we're putting AI into a brain of a robot, and then that robot is thinking and acting like a human. That's what we're trying to do right now. AI gives robots the intelligence to adapt and make decisions. Robots with AI are just machines that follow instructions. Okay, next slide. All right. The goals of AI are understanding, decision-making, and learning. Problem types in AI, generative versus discriminative, probabilistic versus deterministic. We will elaborate on this right here. So the goals of AI, three main goals to achieve human intelligence, like we said, understanding. AI systems need to understand information, process, and make sense of the world around them. For example, AI can understand spoken language like Siri. We all use Siri, of course, or recognize objects and pictures like facial recognition, like I just told you guys, from the cameras, right? Decision making. After understanding the information, AI systems must make decisions based on what they know. So now the AI system has the information, now it needs to make a decision. It has that ability of decision making. For instance, a self-driving car, like Tesla's now, uses AI to decide when to stop, turn, or accelerate based on road conditions, right? There's this camera on the Tesla, or they put these lasers and cameras. It's measured, it's like in less than a second, it's measuring everything and taking pictures of everything around it to see where it's gonna move, where it's gonna do this, where it's gonna do that, not to bump in this car, not to do this, right? And learning. AI gets better over time, like we said, by learning from data and experiences, just like humans. Machine learning allows AI systems to improve their performance without being specifically programmed to do so. So you don't have to go back and program it all the time, right? AI is learning by itself, right? It's built to do that. All right, example. A recommendation system like Netflix learns your preferences, like I gave you guys the YouTube example. Same thing with Netflix, right? It learns from your preferences and suggests what show you might like to watch next. Right? It knows, like, from the cast of the movie you like to watch. Let's say, Amitabh Bachchan's movies. You guys know Amitabh Bachchan? Shah Rukh Khan, right? From India, right? I watch Indian movies, so I can tell that. So if you're watching a certain character or actor, it's gonna see that pattern in your choices, and it's gonna give you recommendations. It's gonna give you more Shah Rukh Khan like movies, or if you like to watch, like, let's say Lord of the Rings. I like watching Lord of the Rings. It's gonna give you more Lord of the Rings movies. You know what I mean? It's just like that. Yeah. All right, problem types. AI deals with various types of problems. Here are two important ways AI approaches problems. Generative versus discriminative models. All right, generative models first. We'll talk about that. These models can generate new data based on what they've learned, like ChatGPT. That's a generative model, right? You ask it something and it gives you an answer. It generates new data from it. Data that didn't exist with it, right? You know what I mean? Example, AI can create realistic images of cats by learning what a cat looks like. So the model already knows what a cat looks like. So if you ask it, hey, can you generate an image of a cat for me? It's gonna generate an image of a cat, right? Generative models can learn the patterns in data and create new examples from those patterns. Also, like we said before. Now, discriminative models. These models focus on distinguishing between two different categories of data. Example, an AI that can tell whether a picture contains a cat or a dog. You give it a picture to the model and it tells you this is a cat, this is a dog, because we trained it on, let's say, 1 million pictures of cats and dogs, of all types, pit bulls, cats, Siamese, this and that, American cats, this. So it can tell whether it's a cat or dog because we trained it on that. We gave it thousands of pictures of cats and dogs, so it knows what a cat looks like and what a dog looks like. And I'll also be showing you guys examples in the future. Okay, probabilistic versus deterministic problem types. Probabilistic type. In a probabilistic AI decisions are based on probabilities. So we're using statistics here, right? You guys know probability for math, right? The probability of something happening versus not happening, the probability of this being this much, or this much, right? In math, right? You guys know that. AI doesn't have a definite answer, but says how likely something will happen, right? So like, for example, AI predicting the weather might say there's a 70% chance of rain tomorrow. It's something like that, probability. The probability of AI can tell you there's going to be 70% rain tomorrow, right? Because they have all these sensors everywhere that take in weather information. And then without doing anything, AI is telling them, information from this sensor, and then it gives you a probability if it's going to rain tomorrow or not. So this is an example. Deterministic. In deterministic AI, the system follows a set of exact rules to make decisions. There's no guesswork or probability. The outcome is always certain if you give it the same input. Example of this will be 2 + 2 = 4, right? No two people will disagree on that, right? It's deterministic, the outcome is always certain. There's no probability in it, just like probabilistic. All righty, next slide. Some more on the history of AI. We'll give a little more elaboration on that so that you guys can appreciate what we have now, right? We're talking back in the 50s and 60s, and they didn't have the computing power we have right now. So we talked about in the 50s, Turing test, we talked about it. Turing proposed a way to measure whether a machine could think like a human. This involves a human asking a question to both a machine and another human. If the human can't tell which is which, the machine said to have passed the Turing test, right? This concept was important because it asked, can machines think? So in this, right here, what the human couldn't answer, the machine answered, right? And we're talking in the 50s too. Like that's what, 70 years ago. Perceptron was the first step function. Perceptron, one of the earliest types of neural networks, which we're going to be talking about neural networks next week. On Thursday. Created by Frank Rosenbaum. It was a simple model designed to mimic how the brain works. Like I said, our brain cells, how they're working, how they're connecting with each other. You know what I mean? It was a simple model designed to mimic how the brain works. The perceptron could learn and recognize patterns in data such as simple images or numbers. So this was like a simple neuron back then, you know what I mean? We're talking 1958 here. And then a step function. The perceptron used a mathematical rule called a step function to decide whether a certain input should be classified into one category or another. This was a foundational concept for modern AI, laying the groundwork for more advanced machine learning and neural networks. So perceptrons were like the beginning of neural networks. It was a simple neural network that could tell if this was this or this is not this. You know what I mean? It was something simple back then because they didn't have, like I said, the hardware we have today. In 1965, we have expert systems, a type of AI designed to mimic human experts in specialized fields like medicine and engineering. These systems used if-then rules. which is like, if this is that, then this. Did you guys use code at all before? Python or anything? You're familiar with Python? You know, if else, it's that concept right there. Solve complex problems and make decisions. Example, an expert system could diagnose a medical condition based on a symptom, much like a doctor would. So we're talking 1965 here. Imagine what we have now. How they work, they contain a knowledge base of facts and rules and use an inference engine to apply these rules to new situations. Though limited, expert systems were an important milestone in AI because they could handle tasks that previously only highly trained humans could do, right? So the best they could do in the 60s was make inferences, like we said, and see if AI can handle what a human can handle in terms of the brain work. An AI winter was in 1984, periods of the 80s when the interest and funding in AI research dropped significantly. This happened because early AI systems couldn't live up to the high expectations that people had for them. Technology wasn't advanced enough, like I said. AI systems were too slow or limited. So in the 80s, it was AI winter. So it was like, you know, the research and everything dropped because they didn't want to fund that. It takes a lot of money, you know what I mean? Like the ChatGPT you guys are using, they used over $300 million of electricity just to train that. Can you imagine? It's crazy. Yeah. So they didn't have this technology back then. So that was one of the obstacles and milestones at that time. Why it mattered? Many thought AI was a failure during this time, leading to less investment and research. Like not enough funding was going into it. However, the ideas developed during this time, like neural networks and machine learning, would later become crucial for AI booms in the 2000s. So in the beginning of the 2000s, they started deep learning, and which we're going to talk about next Thursday and more in the future. In the early 2000s, that's when it started booming. The winter eventually ended when computing power increased and new breakthroughs like development of powerful algorithms and reignited interest in AI. So basically, in the 80s, they were like, there's no funding, there's no interest. You know what I mean? So it had a drawback in that time. But in the beginning of the 2000s, that's when they started. You know, it was like, let's say, resurrected from the dead. I'll say, yeah, basically. Yes. All right. Next slide. Machine learning. So now we're getting into machine learning, right? It's a subset of AI. It uses statistics. You guys know statistics, right? Or math. Statistics are the nuts and bolts of AI, right? Because it's using all this data from tables and you know, and all kinds of sources, a lot of data. Machine learning is how you determine the underlying function that solves a problem, right? AI uses the function solved by machine learning methods to make decisions. You know, you can see this picture right here, Jessica put in. It's how robotic systems and machine learning statistics, they all like fit into this AI picture where it mimics the human brain, right? All right. So machine learning is a subset of AI. It's not all of AI, it's part of AI, right? It's a branch of AI right here. While AI is the broad field focused on making machines intelligent, machine learning specifically focuses on how machines can learn from data and improve over time. Like we said before, you know, over time it's getting more data, it's going to get more improved. You know, we give it more data. Machine learning, you know, gets better at what it does, basically. Examples: AI is like a general brain. while machine learning is the learning process that makes the brain smarter, right? AI is the brain, machine learning is the process that makes the brain smarter. You guys get it? Kind of like that. How it fits into AI. Machine learning is used to find patterns in data, like we said before, and come up with solutions to specific problems. So it's looking for patterns in the data, right? Let's say I give you guys a data set with that's, it's supposed to determine the miles per gallon of a car, right? Data set has weight, the weight of the car, the make of the car, and how many cylinders is in the engine, right? So it's supposed to make a decision. We trained it to find how many miles per gallon it's going to use because we put all this data of a lot of cars from their weight, how many cylinders is in the engine, from this and that. So you know what I mean? It's going to make a decision then how many miles per gallon is that car going to consume, right? Something like that. All right. Now statistics. Why is statistics important in AI? It's the nuts and bolts of AI, right? Statistics is a key part of ML, of machine learning. Machine learning relies on statistics to analyze the data, find patterns, and make predictions. Based on that data. Statistics help machines determine how likely something is, like predicting the weather, like we said, or an outcome of an event, right? It's using all these, like we said before, will a game of ball get canceled or not? That's another application we use in AI, right? Based on what? The data we have. What's the data we have and the statistics? How's the weather? What's the humidity? What's this? What's that? Takes all this data and then determines if a game is going to get canceled or not today, something like that. All right. Why statistics matters. In AI, machines often deal with uncertainty, like guessing how many people will buy a product next month. You'll never know, like it's an uncertain thing, right? I never know how many people are going to buy this product next month, right? But using machine learning, we can give it some data from the past, from past customers, that can kind of guess, like it's going to predict how many are going to buy a certain product, right? Statistics help them figure out most probable outcome based on the data they've learned. Also, probability we talked about, probability of this happening tomorrow or not happening. Chance of rain tomorrow is going to be 50%, 60%. This all is built on data, on machine learning and AI. Everything on your phones basically that we use, right? Based on that. And then algorithms. You guys familiar with this term? Right? Algorithms, like computer algorithms and programming algorithms, right? Our algorithms are the instructions that tell a computer what to do. Like you're telling the computer what to do and what steps to do it. This is the way I want the computer to do. This is my algorithm that like, let's say a programmer or something, say you made a new algorithm for to detect, like, let's say miles per gallon, like I said. You made a new algorithm for it. Someone else may have a different algorithm. So algorithms don't have to be always the same. In machine learning, an algorithm is a set of rules or steps the machine follows to learn from data and solve a problem. Example of that, you're teaching an AI to recognize pictures of dogs. The algorithm would define how the AI looks at different features in the images to decide if it's a dog or not. The eyes, the ears, the extension of the face, all these things, right? It's going to look at all these little things while you train it, and it's going to know if it's a dog or not, right? So it's going to look at everything. The dog's body, its ears, its nose, everything. So then it knows it's a dog or not. Right? Train it on that. So types of algorithms here. This is where, we step into machine learning for real. So supervised learning. The algorithm learns from labeled data where the correct answer is provided. Supervised learning, again, labeled data. So like I said, I have a table that has the weight, make, and how many cylinders in a car, right? Also, I have another column in that table that already says how many miles per gallon. That's what humans tested, right? Now we want to see what the computer says, right? Now, having that miles per gallon is called labeled data. We have the labeled data, right? We already have predicted values that we discovered ourselves, right? So I already know a car that has 4 cylinders, weighs like a ton, and is an Acura or something. It consumes 25 miles per gallon, right? I have that in the table. It's a known fact. It's labeled data and it's there. But we're going to train the machine learning algorithm to tell us to see if this is accurate or not, right? So I already have labeled data there. And then in unsupervised learning, the algorithm looks for patterns without being told the correct answer, right? We don't have the MPG. It's not there. So in unsupervised learning, it's unlabeled data, right? Get this, supervised learning is labeled data. We already have tested data and stuff that we did as humans, right? And then we're going to talk about this more in the future. I'm just giving you an introduction to it here. Unsupervised learning, there's no labeled data, right? So I just have a bunch of data that says, these guys bought 3 carrots, these guys bought 5 gallons of milk, these guys bought this bought that. And it's supposed to find patterns by itself. Basically. That's what we're going to talk about in clustering. And then reinforcement learning is another algorithm. It learns by receiving rewards and penalties for an action it takes. It's called something called the agent. The agent, right? Example, video game. The agent is the guy you're playing with, the character you're playing with. Let's say you're playing a shooting game or a sword game or something, right? The agent is that character you're playing with. There's an environment, which is the environment in the game, right? And then reinforcement learning gives a reward and penalty. If this agent, which is the character you're playing with, picks up like a medicine box, right? You guys seen that in game before? Picks up a medicine box, his energy gets big, right? Goes big. That's important reinforcement learning. He gets hit by someone, the energy bar drops a little bit. You know what I'm talking about, right? Yes, that's a reinforcement learning. There's an agent, and there's an environment, and there's penalty and reward, right? If the agent does good, it gets rewarded, right? If the agent does bad, it gets penalized. So there's a penalty, right? Example is the video game thing that I talked about. All right. Machine learning is how you determine an underlying function that solves a problem. In machine learning, the goal is to find hidden relationships, like we said. I'm repeating a lot to you guys so you guys can pick it up. In machine learning, the goal is to find the hidden relationship or pattern called the underlying function that explains the data. For example, if you have data on students, study hours, and test scores, machine learning can find a function that predicts future test scores. Like I said before, now I have all this labeled data here, and I have students, like I said, how many hours a student puts in, his test scores, and a lot of other factors maybe, and then it predicts for me the future test score of a certain student. Like say it says Avi here studies 10 hours a week. Another student studies 6 hours a week. So and your previous scores also. It's going to predict how good you're going to do in the future, and it might be right or it might be. So like I said, it looks for hidden relationships and patterns. How it works. You give the machine a lot of examples. You give it a lot of data on that. I give it data on 1,000 students. Each student is different from the other. This guy put 6 hours. This guy put 7 hours. This guy's previous score is 90, this guy's 100. So I give it data on like 1,000 students or something. It trains on that, on these 1,000 students. And then when I give it new data that's coming in, it's gonna predict how good the student is gonna do in the future. That's one example. Alrighty. Once the machine finds that function, it can be used to predict future outcomes and make decisions, like I said. So we're talking about here underlying function. Underlying function is the function finding the patterns and similarities in the data. So it can make predictions in the future based on that data. Right? All right. AI uses the function solved by machine learning methods to make decisions. So it takes all these functions then to make decisions. After it finds all these patterns and similarities, right? After machine learning finds the best function to explain a problem, AI systems use the function to make decisions. An example of that, AI machine learning model might learn how to predict whether an email is spam or not. AI uses that information to automatically sort your email into inbox or spam, like emails. Did you get emails in spam at all, right? It knows what to look for inside that email, and then it archives the spam or not. I mean, puts it in your inbox or it throws it in spam, or bad email. All right, the relationship. To summarize here, machine learning figure out the solution or pattern. AI uses that solution to take an action and make decisions. Clear? Good. Next slide. Machine learning. We're still in machine learning. All right. You need an input that is machine readable, right? You need the machine needs data that is readable to it, right? That's why we turn it all into zeros and ones. Because a machine only knows zeros and ones, right? Right. You need an output that is machine readable also. You need to have a reasonable belief that there could be a mathematical function connecting or delineating data between the input and output. You need some sort of mathematical construct that can be turned into to represent the relationship between the input and the output. You need a way to tune that mathematical construct to fit the relationship between input and output also. So we're talking input and output here. What's the input? Like I said again, back to the car example, input is what? Car's weight, how many cylinders in the engine, and the car's make, right? That's the input. What's our output? Miles per gallon, right? That's one example. So we're giving it these three things to look at. And the output is going to be miles per gallon, like I said. So it needs an input and an output, right? All right. You need input that is machine readable. Input. This data you give to the machine learning algorithm to learn from. The data has to be in a format the computer can understand and process. Example, machine readable inputs, text, like social media posts. These are machine readable numbers, like test scores, images, like pictures of cats. These are all inputs, right? Also, another thing, giving it an image, an input is an image of a cat. The output, is it a cat or not? Right? That's the output. All right. You need an output also that is machine readable. Output, this is the result or prediction that the machine learning algorithm generates. Like I said before, in the car example, you give it 3 parameters and it's supposed to give you 1, which is the miles per gallon, right? You give it a picture of a cat, it's supposed to tell if it's a cat or not, right? All right, examples of that would be a prediction like, is the email spam or not? If it's spam, it's going to get thrown in the spam folder. If it's not, it's going to go in your inbox. Classification, like this picture of a dog. It classifies it as a dog or a cat, right? That's another output. Recommendation, like suggesting a new video or to watch, right? Like I said, the recommendation system is going to take in all your preferences, right? stuff you brought before, the stuff you watched before, and it's gonna make a recommendation based on that. You need to have a reasonable belief that there could be a mathematical function connecting or delineating data between the input and output. There's math in the middle. Always, like I said, you know, it's machine learning, input, output. In the middle, there's math going on in there, right? Very complex math, you know, we're not gonna go that deep, but I'm just to give you guys an example, right? Mathematical function. Excuse me. The idea behind machine learning is that there's always a pattern or relationship, like we said before. There's always a pattern and relationship between the input data and the output result. For example, the number of hours you study is the input, like we said. Number of hours you study is input. Could be related to your test score, which is the output, right? I give a model. Hey, Abi put and Anshi, they put 10 hours of studying, so they're both going to get 90%, right? The other two students, they put 5 hours of studying, they're going to get 80% or 70%, right? That's the output. Machine learning tries to find these hidden patterns. Alrighty. Belief in a connection. You have to think there's some kind of mathematical connection between the input and output, even if it's not obvious at first. You don't see what's going on inside the computer, right? But you know there's complex math going on, right? Give it an input, all right, I'm just giving it something and, you know, give me an output, which is a result, right? You know, he studied 10 hours, okay, he's gonna get 90%. She studied 12 hours, she's gonna get 100%, you know what I mean? There's math in the middle. It's actually all math. it's all based on very complex calculus and math. It's undeniable. You need some sort of mathematical construct that can be tuned to represent the relationship between the input and the output. Mathematical construct here, we're talking to the model. It refers to the model or equation that's being used, right? In the machine learning algorithm, and it's used to represent the relationship between the input and the output. Just like regression. You guys took regression at school, right? Linear regression, right? You guys can see here, multivariate linear regression. So like this, the input here is an independent variable. It doesn't depend on anything, right? But the dependent variable is what we get up here, right? So let's say I put in, he studies 10 hours. Simple linear regression, y equals mb plus x, right? That's it. That's very simple math, right? I put this is just like another. I'll put an example here as like, you know, you study 10 hours, so you're gonna get 90%, right? He studied 1.5 hours, he's gonna get this. Simple linear regression. This is regression machine learning, right? Something like that. All right. All right. Example, if you have data on how much people like certain TikTok videos, a model could represent the relationship between the video's features, which is the input, and how much it's liked, right? So how many people commented on that? How many comments are in that video? 100,000 comments, right? And like, let's say 200,000 likes, right? It knows this video is gonna do good. Why? Because it has this data on it, right? The input is what? The 1,000 comments and the 2,000 likes. You know, that's the input. Video is gonna do good. So it gets recommended on YouTube or TikTok to other watchers or viewers, right? All right. The model has to be flexible, meaning it can be adjusted to better fit data. So I'm not just gonna build a model and leave it like this, you know what I mean? It has to be flexible, it has to be editable, so I can edit it later in the future, right? Because it might not, because we might make something new, right? We might make, like, let's say comments, likes, dislikes. They might create a dislike function in the future, so I'm gonna have to go back to the model and edit that, right? So it can take in another parameter of data that it's gonna make an output based on, right? You need a way to tune the mathematical construct to fit the relationship between input and output. Tuning, the algorithm needs to be trained using data, just like a guitar, right? You want the guitar to give you out a good tune. So you have to tune it right? From the things on the side. You have to like tune the chords and see how good it becomes after that, right? It's the same exact concept. You know, and we're gonna talk about it more in the future, like I said. But that's like a basic example right there. This is done by adjusting parameters in the model until it makes good predictions, right? So let's say I trained a model, right? But its accuracy is like 50%. Am I just gonna put that out there and use it? No, of course, we would have like a model that's like 95%, 99% accurate in what it's predicting, right? You know what I mean? So we don't want to just throw out any model out there that's gonna like, if I give it a picture of a cat and a dog, it says this is 50% likely a cat, but it's a dog. So it made the wrong prediction, right? So we have to keep tuning these models. I'm gonna actually show you guys all of this in code in the future and show you examples of it. This is just an introduction for today. And show you how these parameters are tuned, just like a guitar to give you out a nice melody, right? So it's the same concept, basically. All right, example of this in a TikTok case, the algorithm might be tuned to show certain types of content, right? Like funny videos based on what people engage with more. If you're the kind that likes to watch funny videos more, it's gonna show you more funny videos, right? I tuned it very well. I tuned the model very well. So you guys are getting a picture of how it fits into technology now, right? Right? So I trained it so well and tuned it very well that it's gonna give me a 99% accuracy. You know what I mean? And that's what makes a good model from a bad model. You know what I mean? It's gonna give me 99% accuracy that this guy likes funny videos, that she likes, action videos. You know what I mean? Same concept. Example is TikTok Shorts. I don't use TikTok that much, but I don't know if you guys do. But I just put it as an example. Same thing with YouTube and all the other apps. TikTok uses machine learning to recommend videos, like I said, TikTok Shorts. That it thinks you'll enjoy because you watched a lot of funny videos. So it thinks you're going to enjoy this funny video. So it's going to show it up to you on the screen, right? So in this example, what's the input? Algorithm looks at things like what videos you've liked. What did you press like on? Is it a funny video? Okay. How long you watched the video before scrolling? How many hours did you put into watching the video? All of this stuff goes into the model and it then makes that prediction. Output based on the input that we talked about. The algorithm predicts what type of video you're most likely to watch and enjoy, right? So based on this video you liked and how many minutes you put into watching it, it's taking all this data from the back end and then it's going to give you recommendation based on even stuff inside the video now. Can you guys imagine that? Like now it's stuff inside the video. It knows what's inside the video. It knows it's going crazy. It's like this stuff is still advancing at an astronomical rate, right? Because like I said, now we have the hardware. Now we have processors that can process this much very complex stuff, And I think if they had this stuff back in the 80s or in the 90s, we would have been like on Jupiter right now or something. Just kidding. All right, mathematical function. There's a relationship between the features of the video's topic, its length, and the creator of the video, and your engagement, right? These are all inputs. You're liking, did you comment on it? Are you still watching it? These are all inputs. And it's all happening in nanoseconds. This is all happening in like a split of a second. Can you guys imagine that? It's crazy, right? The machine learning model finds a pattern and uses it to suggest more videos for you, like we said before. Your inputs are, I clicked like, I watched it 10 minutes, the maker of the video is such and such, you know, and recommend more of that for you, right? Tuning the algorithm, like we said, like tuning the guitar. As you keep watching videos, the algorithm keeps learning from your behavior and improving its recommendations by adjusting its prediction. Right now, they don't even have to go back and tune it. It's tuning itself. Can you guys like imagine that? It knows from people's behaviors and what they're watching and this and that. It tunes itself to you based on your personality, based on what you like, based on what you don't like that. All right, next slide. Why would I use machine learning? Is the time and money to collect the data and train the model going to outcompete the current solution in monetary cost and time cost? Like I said, it takes a lot of money to train a model to do something. Like ChatGPT, for example, you know, like I told you guys, it took a lot of time and money to train that ChatGPT, like, and electricity. It's all in electricity, right? So it's a big bill to train one of these super models. Do we not currently have a solution to the problem? Have initial features that relate to the problem? Is there meta research questions regarding the limitations of the models? Is the accuracy potential of the model not matched with what is needed? Example of misuse, using machine learning to determine the color of something. We can use the encoded data in the image file much more quickly. Correct use of machine learning, using 95% accurate machine learning to identify plants for a hobbyist botany nature walk. An example of misuse, using 95% accurate machine learning to identify non-toxic plants that you can eat. So basically, it's like saying machine learning is a two-edged sword. You can use it right, you can use it wrong, right? An example of good using it is going to be like, yeah, 95% accuracy model that determines plants for a botanist. You know, I like to take walks in nature and then I take pictures of certain leaves or plants. It has 95% accuracy to tell me this plant is this plant. It's like it's parsley. This is you know, ginger. This is that. You know what I mean? That's a good example of using machine learning, right? And an example of misuse would be using 95% accuracy machine learning model to identify non-toxic plants you can eat, right? Because you might, if it's not 100%, you might pick up a toxic plant and eat it. Right? I'm taking pictures of these plants in nature and I pick up a certain mushroom, I eat it and I die. You know what I mean? So that's an example of misuse, right? So the time and money to collect the data and train a model going to outcompete the current solution, because it takes a lot of money and time to create a model and train AI. It takes a lot of time and money. But with today's hardware, like I said, it's becoming easier. Before using machine learning, you need to ask, is it worth the money? You know, before I spend 300 million on making ChatGPT, you know, and all this electricity, is it worth the money, right? Just an example. Collecting data and training a machine learning model can be expensive. You know, I go to data banks and ask people and ask these like data banks for their data. You know, they want money too for that data. You know, sometimes they pay billions and millions for that data. Examples: is cheaper to use machine learning, or is there another solution to the cost less? Time, also time. It takes a lot of time to train these models. Training a machine learning model also takes time, from gathering data to fine tuning. You should ask, will using machine learning save more time than the current method? So if we're trying to make a new method for a model or something, excuse me, will it save us money, right? Will it save us time? Because like I said, it takes a lot of time and money to train these models. It's very costly. Do we not currently have a solution to the problem that have initial features that relate to the problem? No existing solution. Machine learning is useful when there's no good solution to a problem, but yet you have data that might help solve it. If you know some features like patterns or variables that could help, machine learning can use them to create a solution. Example: you may not have a way to identify rare plants, right? But you have data on these features of these rare plants. I don't know if it's a rare plant or not, but I do have its size, the leaf shape, the color, and everything. So when I build a model that takes pictures of plants and tells me what this plant is, whether it's toxic or not, I have that data. You know what I mean? That's useful, but I might not be able to train that model because it takes a lot of time and money, right? Yes. Is there a meta research question regarding the limitations of the model, understanding the limits of machine learning? So the limits of machine learning here, sometimes researchers want to use machine learning to test its boundaries and understand its limitations. How far can it go, right? What's its boundaries and limitations? This could be part of a bigger research question where you're asking, how well can a machine learning model handle this problem, right? You might use machine learning in research project to see where it struggles or what kind of problems it can solve well, right? So I'm putting the model to the test now. I built it, I trained it, I spent all this money on it and time, of course. So now we put it to the test. Is it struggling? Tell me whether this plant is toxic or not, or is it not? They go through a lot of tests basically before they publish them out for people to use. Yes. Is this accuracy potential of the model not matching what is needed? Accuracy issues. Like I told you guys before, the accuracy issue, right? We don't want to use a model that's 50% accurate when it's doing something really, really important and dangerous, right? Let's say going to space or toxic plants or stuff like that, right? Sometimes machine learning models aren't accurate enough for the task at hand. If the model is only 95% accurate, it might not be good enough. For certain cases, even 95% is not good enough. You know what I mean? It needs to be 100% accurate sometimes, or 99.999 something accurate, right? Depending on your need, If it's toxic plants, it has to be 100% accurate, telling us toxic plants to eat or not. If it's like MPG of a car, you know what I mean? 98% would suffice, 99% would suffice, you know what I mean? If it's looking at dog and cat pictures, from me, my experience training models, 70% was enough, and 80% was enough. It did very good with telling whether it's cat or a dog, A lot of examples. An example of that you're identified here, like we said, if you're identifying dangerous or poisonous plants, even 95% accurate model could be too risky. It has to be 100% reliable, right? Because these missing 5% can, give you like I said, a bad mushroom. You eat it, your face swells, you die. It's crazy. Yeah, and we don't want that happening, of course. Examples of misuse, like we said, using it to determine the color of something. Machine learning shouldn't be used for tasks that can be solved much more easily. So stuff that makes sense in nature. You don't need something to tell you that this is a white table and this is a black board and this is the what I mean. Stuff that makes sense. Basically. Figure out the color of something from images is unnecessary because the color data is already stored in the image model. You can read the color code without needing a machine learning model. So it's like an unnecessary model. Why would you build it, right? And spend all this money and time building something like this? Why is it misused? Because machine learning takes too much time and effort to build one. It takes a lot of time and effort to test with it and tune it, like I said, and put all these things into it. It takes a lot of time and money. So you have to put it into something necessary and useful, right? Example of correct use, like we said here, using 95% accurate model to identify plants for hobbyists on a nature walk. This is not a dangerous thing, I'm just a plant hobbyist. I like plants, so I just like to take pictures of plants. It's going to tell me, whether this is parsley, this is ginger, this is that, It's not, there's low risk in it. Not like the poisonous plants, right? So 95% accuracy would be good for us, right? And I'm going to be showing you guys more examples in the future. Why is this good to use? Let's take a simple, and it takes, the risk is not high, I'm just looking for plants in nature, and if it doesn't tell me the right thing, it's not going to kill me. So using an example of misuse here, like we said, the 95% accuracy on a toxic plants. So we don't want to have a 95% accuracy model looking at toxic plants for us, right? You don't want to die eating something. Because an app told you, like, eat this plant, it's fine, you know. It's crazy. You don't want to die from something like that, right? All right. So AI, sky high view of machine learning and AI here. So I don't want to go too like deep into this because I don't think we have enough time. We have like 20 minutes left. And let's see. And okay. At its core, the goal of AI is to solve problems. Like we said, it's to solve humans' problems. Looking for smarter solutions for real world challenges. You know, different types of classes and problems here. We're going to talk about classification, which I'm going to be showing you guys also examples in the future. Classification, it sorts data. Classification basically is it a dog or is it a cat? Is it a human or not a human? That's what classification is, right? Is it this or that or this or that? That's what classification is. Regression, predicting numbers, just like based on patterns, just like the MPG. Regression usually works with numbers, right? I give it the information, how many miles per gallon is going to put, right? Just like also the college admission, right? I give it some numbers. Is this guy going to get admitted in college or not? What's the chance of him getting admitted? Right? It's going to give me a number. But classification is this a cat? Is this a dog? Right? Is this a human? Is this not a human? Like that. Clustering, like I said, grouping similar things together. Just like the milk and eggs, right? These guys buy milk, eggs, this and that, put them in this category of customers. These guys buy this, and that, put them in this category of customers. Basically, this is clustering, putting each one in their own cluster, right? Basically. Or putting people in their groups. Or is another example. You know, these are the very smart guys. This is their cluster. These are the medium smart guys. This is their cluster. These are the not so smart guys. This is their cluster. Basically, something like that. And each problem of these requires its own approach, its own algorithms, its own everything, which I'll be showing you guys also examples in the future. All right. So the different learning methods here, the different problem, each problem has a different learning method, like we said before. Common learning methods, we said, supervised learning. Supervised again, labeled data. Always remember by that. Supervised learning is labeled data. Unsupervised learning, it's learning patterns, but it's unlabeled data, right? Like I said here, finding groups of customers with similar shopping habits, right? So I put them in this group of customer, I put these guys in this group of customer, because these guys buy a lot of milk, these guys buy a lot of carrots, this and that, right? Reinforcement learning we talked about, through trial and error, by receiving feedback from actions, like robots learning to walk by getting reward for successful steps. Right? So you're telling a robot, reinforcement learning, we said, I gave you the video game example, right? And so the robot does good, I'll give you some lubrication. You know what I mean? I'll give you more fuel in the future, you don't do good, you don't get any of that. So the robot learns from that. This is a bad thing, this is a good thing to do. This is a bad thing to do. That's reinforcement learning. We talked about that. All right. Multiple machine learning algorithms can be used into one model. For each learning method, there are machine learning algorithms or models that can be used to perform a task. Why are there different models? Different models are based on different mathematical ideas and different problems. Why do we build different models? Because we have different problems to solve, right? Some models might work better in specific situations, but they fit the problem structure better than the others. For predicting house prices, for example, a linear regression model, like we said, is going to be good, right? A neural network of that may be better. We're going to talk about neural networks next Thursday. But like I said, predicting a house is a linear regression. Okay? It's giving you a number. That's why it's regression. It's not classification. Okay, models represent different mathematical constructs. Each machine learning model represents different mathematical constructs, like we talked about before. Some models might use simple math, like straight line equations, like the ones I showed you. Simple math, y equals mb plus x, right? On the graphs, regression, simple regression. The choice of model depends on the problem's complexity and the type of data you have. Some problems are solved better by one model than the other, You don't need all these models can solve you like simple problems. Not all models are equally good at solving problems. Some problems may be better solved, one model than the other because some models handle the data better, basically. If you want to predict a curved pattern, like a shape of a circle, using a simple linear model would predict straight lines won't work well. You would need more complex model to handle something like that, like this, like this curved shaped circle right there. If it's like, it's gonna tell me whether it's curved shaped or not. I can't use a regression model to I need something more complex. So that's where deep learning comes in, and we're gonna talk about that on Thursday. Examples, learning the function of a circle. Imagine trying to teach a machine to learn the function of a circle. If you only allow it to use a single linear function, which can only draw straight lines, you won't be able to do that, represent the problem, because circles are curved, right? It's not linear, right? This shows how important it is to choose the right model for the task. A simple model may fail than other for complex problems like these. So to summarize, AI tries to solve different problems using specific learning methods. Each method has many algorithms and models to choose from because some models work better for some problems than the others. Understanding which model fits the problem is key to successful machine learning, which will be discussed more in the coming weeks. All right. So I won't go too in depth here, but I will go quickly through these. As for types of learning, we talked about supervised, unsupervised, semi-supervised, and self-supervised. Talked about all these in the previous slides. So we said unsupervised learning, we said labeled data, right? We have labeled data here, right? Inputs and output, you have the data, but you don't have the correct output categories. You have to find the structure. The goal is to discover patterns, like we said, in the groupings of your data. Example, grouping customers based on their purchasing behavior without knowing in advance what the group should be, right? This is unsupervised, and this is going to be a clustering problem. Self-supervised, it's learning where the data provides its own labels of ground truth internally. The ground truth, like I said, is the actual data we have, right? I already have information on how many miles per gallon the car is going to give. Input and output, the system generates its own rules on the data itself. Also fill in the blank. The model learns by predicting parts of the data from the other parts. Example here, predicting the missing words in a sentence based on surrounding words, right? So in a self-supervised scenario, it's going to predict, for example, there's a missing an underlined statement that's missing, and it's going to predict what it is based on the context, the words being provided, right? So, supervised learning with labeled data, like I said, supervised labeled data always, remember that. Where the correct answer is provided, you have the data with no labels and categories. The model learns by finding patterns between the input data and the given labels. Training the model to recognize cats and dogs, like we said, in supervised, where the image is labeled either cat or dog. So they're already labeled as cat or dog. Supervised learning here. Semi-supervised learning, it's learning with a mix of labeled and unlabeled data, right? This is like a mix between supervised and unsupervised learning, right? The input and output. Some data points have labels and others don't have, right? Ground structure search. The model uses labeled data to help understand the structure and pattern in the unlabeled data. It's basically just like clustering. It's trying to see the pattern for itself because it's a mix between labeled and unlabeled. So it's working on the unlabeled part. Example, using a small set of labeled images to help classify a larger set of unlabeled images. Right? Ground truth is, I would say the actual, I was trained on it as actual. I didn't use the ground truth term before, but I knew it as actual. It's probably just that's how Jessica was trained on it, ground truth. The type is, that's the actual data we have. Like I said, I have actual data on how many miles per gallon the car is gonna put, and then we're trying to train a model to predict its own values, right? Correction information or labels used as reference in machine learning. In supervised learning, ground truth is labeled data, like we said, the MPG, for example. And here, example labeled as cat or dog for a classification problem. In unsupervised and self-supervised learning, ground truth is not used. Instead, patterns or rules are discovered without predefined answer. Like, we don't have actual data, like I said. In unsupervised, it's supposed to find these labels by itself. It's supposed to see these patterns to see where each category falls into. Purpose of it helps evaluate the accuracy of a model by comparing its predictions against the known correct labels. All right. To summarize, unsupervised learning, no labels, it discovers patterns on its own. Right? Just to summarize it, no labels, it discovers the pattern on its own. Self-supervised, data provides its own labels, predicts missing parts. Supervised uses labeled data, finds patterns based on known labels. Semi-supervised, mix of labeled and unlabeled, using labels to understand the structure of the unlabeled data. So we're using the labeled data to understand the structure of the unlabeled data, right? The ground truth or the actual data, I just like to call it actual data. The actual labels or information used in training the models. Like I said, the example is the MPG that we already have from testing. Alrighty, so continued. Jessica, can I ask you something?
Of course.
So is it till 7:30?
It's till 7:30. If you, sorry, I'm getting feedback from the room.
Should I?
If you want to finish this slide, and then I'll talk about the project, and we can wrap up and pick up those last slides for the next slide.
Okay, sounds good. Sounds good. I can finish this slide. So, reinforcement learning, like we said, this type of learning where AI learns by interacting with the environment. Like I said, there's an agent, there's an environment, and it's receiving feedback based on its actions. It's often described as toddler learning, like a little kid learning something, because like a toddler, AI learns by trial and error, right? Like I said, you do the good thing, you get reward. You do the bad, you get penalized, right? That's exactly how reinforcement learning works. It's just like, a kid is gonna play with matches, burns himself, he knows it's a bad thing, that's a penalty, right? A kid gets good grades, his dad gives him, a present, so he wants to do that again, so he will get good grades to get more presents. The penalty would be like I said, a toddler played with the matches, he's not gonna do that again because he got penalized. That's reinforcement learning. Alrighty? And receiving big feedback based on its actions, it's often described as toddler learning, like we said. The AI learns by trial and error, trying things out and getting rewards or penalties based on what it does. How it works, the AI takes action and learns which actions are good and which are bad, like I said. Over time, it learns to repeat these actions that lead to a reward. I'm going to repeat the action that leads to a reward. It's something in psychology also, human psychology. You do the good things so you can get the good. You avoid the bad things so you avoid the bad. You don't want to get that. All right. It learns to repeat actions that lead to rewards and avoid actions that lead to penalties. Each attempt at a task builds on the previous experience, improving the AI's performance. Where it's used, reinforcement learning, robotics is a common field where reinforcement learning is used Because robots often need to interact with the world and learn like the world around them. Sorry, excuse me. And learn how to accomplish tasks like like navigating a room or picking up objects. Right? An example would be imagine a robot trying to balance on two wheels. Each time it falls over, it receives a penalty. Right? And when it stays balanced, it gets reward. Over time, it learns how to stay balanced longer because it's going to get more rewards. Like I said, you get the better grades, your dad gives you a better gift. You know what I mean? He's going to give you an iPhone 16 or something if you get it. But you won't, like, let's say you won't go out, you won't skip school and leave because you know your dad's gonna, you know, let's say, put you in a room for a week without anything. You know what I mean? You want to avoid that, right? So you do the good stuff to get the reward. You avoid the bad stuff to avoid the penalty, right? And then we're gonna end here with few shot learning. I'll do the rest of them on Thursday with you guys because we don't have enough time. Okay, so for few shot learning is when AI is trained to complete a task only using only a few examples of how to do it. This type of learning is important when there's limited data. We don't have enough data, okay, or examples available. How it works. The AI is shown just a few examples of tasks, like identifying types of birds. You know, this bird is this is an owl, this is an eagle. And it's expected to make predictions about new examples by comparing them to the ones it has seen. I don't have that many pictures of owls and birds, and eagles. So I'll use few shot learning in this example because I don't have enough data. I only have 10 pictures of eagles and 10 pictures of owls, right? So we use a few shot learning approach. Alrighty. It uses probabilistic learning. The AI doesn't always know for sure, but it gets its basis on how similar the new data is to the ones it learned. So I give it an eagle picture, and it only got trained on 10 eagle pictures, not 1,000. You know, so I give it an eagle picture, it's gonna say whether it's an eagle or not. So this is where few shot learning comes in handy. Where it's used, it's useful when there's not a lot of training data, like we said. It's good for tasks like image recognition or classification, you know, like on your phone. You don't have to give the phone like 100 of your face images to know that, you know, only a few shots of your face is gonna tell you know, because you have little data, not a lot of it, right? Or classifications where collecting large data sets might be difficult. If the AI is shown just a few images of different birds and then asked to identify a new bird image, it makes a prediction by choosing the bird that it's most closely to it resembles, even with limited examples that AI makes probabilistic. So if I give it falcons and hawks, kind of look like eagles, right? Falcons and hawks. So if I give it a picture of a falcon, while it's trained only on 10 eagle images, you know, it's gonna say it's an eagle because it's the most closer to resemblance, right? All right. To summarize, reinforcement learning, the AI learns by interacting with its environment, making mistakes, and improving over time through feedback. It's used in robotics and in real-world interactions. Few-shot learning, the AI learns to perform tasks with just a few examples. Often, when data is limited, we don't have that much data available to train the model. Like classifying bird species based on small numbers of pictures. These learning methods are more specialized than traditional supervised and unsupervised learning, offering powerful ways for AI to tackle complex data or data limited tasks. And here we run out of time, and I'll leave the rest to just.
All right, thank you so much. Can we move to the class project slide?
The project slide?
Yes.
Yes, here it is.
So thank you everyone so much for being here tonight. I wanted to introduce the class project to you. It's going to be happening in 5 different parts. Each one will be due starting 1 week from now and then every week after that. The purpose of this project is really to try to give you guys some hands-on experience about how you would plan a machine learning study around a given scientific problem. And that's as broad as it's going to be. If you have a great passion for robotics, you have a great passion for chemistry, you really like astroscience, whatever scientific problem you're interested in, you can make your project around that. The 5 checkpoints that we're going to have are going to start with problem selection. So for next week, you're going to look at what is the problem that you're interested in, who's affected by that problem, and a bunch of other questions that are available in the Google Classroom that you guys are all a part of. And if you're not, stop by and let Nagi know and give him your email so that we can make sure you get added to that class. We're going to talk about the data, the models, and the opportunities and limitations of that particular problem in the models you might make around that problem. So you're not necessarily going to be responsible for coding up this problem within 6 weeks. That's a little much to be asking of you guys, but we want to make sure that you have the tools to evaluate the problem to determine, is machine learning what I should be doing for this problem? Is it going to produce the types of results that the people who care about this problem want in the end? So all of those checkpoint assignments are already available on the Google Classroom. You can complete them as early as you want. They do have deadlines, so every week starting next week. But if you want to complete them all in one shot, you are more than willing to. And if you have any questions, whether that's about what your project should be around or any other questions about the course, feel free to either email me or ask Mr. Nagi here. We'd be delighted to help you with any of that.
Absolutely.
All right. Any questions from you guys?
Any questions? Was everything I explained clear?
Yeah.
Did you guys like the lecture?
Yeah.
All right. So no questions. I guess for homework, should I assign them to? They already know Python.
Well, I don't
Not a lot of it,
I don't know.
but I'll give you guys a homework assignment to at least watch like an introductory on Python and machine learning.
Okay.
Right? Because I'll show you guys in maybe Thursday or next week some examples where you guys can like see this stuff in action, you know. I'll try to show you guys how to like how it's lined you know, how it's lined out, how it all works and gets put together, you know. So you guys have a better idea.
Okay.
And so that assignment you will be able to find on the classroom. We'll have a couple links for YouTube videos that can teach you a little bit about Python if you've never dealt with it before.
All right.
All right.
So we're good?
Good on my side. If there are no questions, then looking forward to seeing you guys on Thursday.
That's good.
Thank you. Thank you.
See you guys on Thursday. It was an honor to have you here all today. So I'll see you guys on Thursday.
Thank you.
Thank you very much.
Thank you.